Hello. 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 Afroz Sultana Ayeng Isriwali Chinna then Ramya M Manjula SSL Tulasi Sri Lata. Yeah. Hello. Hello. Good morning.
Sir, good morning, sir.
Can we start? I am V. Srinivas and Dr. Vijay Kumar. He comes at 4:30. Okay. I have some work after 4:30. So we have exchanged our periods. Okay. I am Srinivas and I'll teach topology in this period from 10:30 to 12. Okay. Yeah.
Okay, sir.
Yesterday I was discussing some questions from the paper 2019. Okay. Again, I'll continue from the same paper, right? Yeah. I'll take a question and try to explain the answer. That is this 2b. Let x and y be metric spaces. Let x and y be metric spaces. Right? And then A be a non-empty subset of X. A contained in X, B non-empty. Okay. If F and G are continuous mappings, if F comma G are continuous from X into Y, such that F of X is equal to G of X for all X coming from capital A, show that F of X equal to G of X on A closure. Okay. or for every x belonging to a closure. Right. So I will, yeah, I want to do this first in this period. Let x and y be metric spaces. A be a non-empty subset of capital X, and then if f and g are continuous functions from x into y, such that f of x equal to g of x for every x belonging to capital A, show that f of x equal to g of x for every x in a closure. Okay. So, see, before doing this question, I want to explain you some basics, right? So here we have two metric spaces x and y, and right, and then A is a subset of capital X, and we are talking about, yeah, if two continuous functions agree on the set capital A, then they have to agree on a closure also. In fact, yesterday we defined a closure, and we saw that it contains the set capital A. Okay. Can anybody remember how we defined a closure? Can anybody tell me how we defined a closure? Hello? Hello? Friends, can anybody tell me how we defined a closure yesterday? Hello? Is there anybody?
Sir.
Can you tell me how we defined a closure? Even if you're looking into book, you can tell me. If you can't tell without seeing. How did we define a closure yesterday? It is intersection of all f.
Smaller supersets of A.
All super subsets
of A.
No, all super subsets f of capital A, such that f should be what? What kind of sets? F have to contain A, and f has to be closed. Okay, f has to be closed. You have to take the intersection of all closest supersets of A. Okay, f has to be a superset of A, and also f has to be a closed set. That's very important. F has to be a closed set. Okay, intersection of all closed supersets is defined to be a closure. Okay, that's how we defined a closure, right? Yeah. Now, yeah, and on R, on the number line R, okay, on the number line R, if you take an open interval, an open interval, right, where A and B are real numbers and A is less than B, and you can show that it's a closure. Its closure is what? Can you tell me what would be its closure? Before that, I should tell you one point. In fact, we can show that A closure will be equal to A union derived set. It's a derived set. A closure, this closure, the closure of A can be shown to be equal to capital A union derived set of A. What is derived set of A? It is set of all limit points x belonging to capital X. So X is a limit point of capital A. Okay. A derived set of A, capital A is defined to be set of all points x coming, small x coming from capital X, as that X is a limit point of capital A. What is the limit point of capital A? What is the limit point of capital A? If X is any metric space, right? This is a metric space. And then if A is contained in X, how do you define its limit point? How do you define its limit point? X belonging to, let X, small x belong to capital X. X is a limit point of A. How do you define this? It is, right? X is said to be a limit point of capital A if every open neighborhood of X intersects A at points other than X. If and only if every open neighborhood of X intersects capital A at a point other than, it need not be points, at a point other than capital X, small x. Okay, X is said to be limit point of capital A if and only if every open neighborhood of X intersects capital A at a point other than X. Okay, so I'm talking about this number line, this R with the usual metric, that is the Euclidean distance metric, absolute value metric. Okay, this is a metric space. This is a metric space. Out of this metric, you get the usual topology. Okay, and in this metric, what is if I take a limit? If I take an open set, an open interval becomes an open set. So this open interval is an open set. And how about its closure? What is its closure? Right. So my set is capital. If I call this open interval capital A, what is A closure? It's this one. Yeah. So if you take open interval, right? Each point of open interval, if X is in right. So you are in this situation. This is an open interval. AB is an open interval, right? AB is an open interval, and X is let X be an intermediate point. Let X be small x be an intermediate point. Okay, you may call you may take a particular point X naught. Okay, this X naught is an interior point. Around X naught, you can take a small open interval of right which is for which this X naught is midpoint, such that this open interval is completely inside this open interval AB. Okay, therefore this X naught becomes an interior point of AB. For this right, if I call this capital A, if I name this open interval capital A, the set of interior points is denoted by A power 0, right? And therefore X naught becomes an interior point of capital A, right? And in fact, in this situation where this modulus value is a metric, okay, out of this you get a topology which is called usual topology on the number line. In this topology, every interior point becomes a limit point. X naught becomes a limit point. Limit point means set of limit points is denoted by derived set of A. Okay, every limit point, every interior point of this on the number line under this usual metric, under the absolute value metric, every interior point becomes a limit point. Therefore, an interior is contained in the derived set of A. Okay. Therefore, and then what I was saying. We can show that A closure will be equal to A union derived set of A. Yesterday we defined A closure to be intersection of all closed supersets of A. That can be shown to be equal to A union derived set of A. Okay. Here you have a topology. Right? In every metric space, X is a metric space. So every metric induces a topology that is called usual topology on X. In that topology, right? You have limit points concept, and then set of limit points is denoted by derived set of A. Then if you take the union of A and derived set of A, we can show that is equal to this this intersection, which is A closure. Okay, so we can for this open interval AB, every point is an interior point. Every point is an interior point. Therefore, this open interval A comma B is a subset of derived set of A. Every point is a limit point. Every point is a limit point, interior point, and every interior point becomes a limit point. That's how each point of this open interval is an element in derived set of A. And other than this, these endpoints, right? Let me use different color, green. Yeah, these endpoints also become small a and small b. They also become limit points. They also become limit points. So you have that A closure of A union B. closure of the open interval A union B is the closed interval A comma B. Okay. Each interior point is a limit point, and even the endpoints of this open interval. For this open interval, endpoints are small a and small b. They also become limit points. And in fact, okay, so closure will be equal to this. In fact, you have what you said. We said a closure is equal to A union derived set of A. Okay. A union derived set of A. So this closed interval is a subset of derived set of A, and A is also a subset of derived set of A. So you have, right, A is contained in derived set of A. So in this particular case, when A is open interval, you have A is contained in derived set of A. So A closure will be derived set of A. Okay, A closure will be equal to derived set of A, and derived set of A will be equal to this closed interval. Okay. Right. So that's how for open interval, the closure will be a closed interval. That's what you have to understand. Okay. In R2, if you take an open rectangle, in R2, if you take an open rectangle, okay, if you take an open rectangle in R2, right, the points in this open rectangle, all these points, okay. These points will be forming an interior of this open rectangle. If I call this B, if I call this open rectangle B, so B will be, interior of B will be itself, okay? And its closure will be B union, right? Its closure will be this closed rectangle, right? Closure rectangle, that will be B union this circumference. If I call this circumference C, right, the perimeter, it's not circumference, it is perimeter rather. If I call the perimeter C, it's B union C. Okay. If B is the set of these points which are in this rectangle but not on the perimeter, and then that is open rectangle, and its interior will be itself. Okay, and then you can show that its closure is equal to that open rectangle union the perimeter. C is the perimeter. Okay, right? This is C. This is C. This is C. Right, and and the union of these two will be B closure. Okay, closure of open rectangle will be the closed rectangle. Means it is the open rectangle union the perimeter. That's what you have to understand. Similarly, in R3, if you take an open sphere, its closure will be closed sphere. Okay. Yeah. Now let us come back to this question. Let us come back to this question. Let X and Y be metric spaces and A be contained in X be non-empty. Okay. Let F and G agree on capital A. Okay, then we can show that F and G agree on A closure. And in fact, we are saying A closure equal to A in derived set of A. On this set, F and G are agreeing. We have to show that they agree on A closure also. Means we have to show that F and G agree. Means they are equal on derived set of A also. That's what we have to show in this question. So let us take a point X from here. And for that point, let us show that F and G coincide. F of X equal to G of X. Okay, so that's how we proceed. Yeah, so yeah. Now, so we have F is mapping X comma D into Y comma D dash, right? And A is a subset of X, and we have F and G is also a mapping from X into Y. Okay, these two are metric spaces, and A is a non-empty set. A is a non-empty set subset of capital X, and F and G are coinciding on A. F of X is equal to G of X on capital A. Means for every X belonging to capital A. Okay, and then we have to show that they agree on A closure also. Okay, claim F of X is equal to G of X for every X belonging to A closure. Okay, and we observe one thing. We have A closure. Okay, this is all answer. I'm writing answer for that question. Okay. Yeah. we have A closure is equal to A union derived set of A. A union derived set of A. Okay. And on this F and G are agreeing, we have to show F and G agree on derived set of A. So let X belong to, or rather X naught belong to derived set of A. Okay. Let us take a point X naught from derived set of A. Claim F of X naught is equal to G of X naught. Okay. This is a general point. X naught is a general point. We want to show that F and G take the same values at X naught. Okay. So X naught is in derived set of A. So from here you get that there exists a sequence from capital A which converges to X naught. So this implies X naught belongs to derived set of A. Implies there exists a sequence Xn n equal to 1 to infinity converging to X naught. Okay. Right. There is a sequence Xn in A. There exists a sequence in A. You may call it An as well. You can give any name. You can call it A. Okay. To show that that this is coming from capital A. There exists a sequence An n equal to 1 to infinity in A such that this sequence An converges to X naught. Okay. This happens because X naught is a limit point of capital A. Okay. There exists a sequence An in capital A converging to X naught. Okay. Next, we have this situation. An is converging to X naught. Okay. We have got a sequence. In capital A which is converging to X naught. Now F is continuous. So F is continuous. F is continuous on capital X. So F and A is capital A is contained in capital X. Okay. F is continuous on capital X. So F of An converges to F of X naught. So F of An converges to F of X naught. Okay. Because F is continuous, it preserves convergence. So F of An converges to F of X naught. Similarly, G is continuous. From here, you also get that G is also continuous on capital X. So G is continuous. So that gives you that G of An converges to G of X naught. Okay? Because G is continuous on capital X, G also preserves convergence. Means G of An goes to G of X naught. Okay. Now you subtract this sequence from this sequence, from these two. Okay. From these two, this and one imply that you subtract this from this sequence from this. You have F of An minus G of An will be converging to F of X naught minus G of X naught. Okay. Because right. Right. The question is, can you subtract? You don't know whether there is subtraction defined on X or not. So you should not do that. 1 minute. You should not try subtract. We don't know whether it is allowed or not. Okay. So you have to do like this. Yeah. You start with F of X naught, and this is limit of F of An as n goes to infinity. Okay, and this is limit, and An are coming from capital A. So F of An equal to G of An on capital A. So it is for F of An you can take G of An because on capital A F and G are same. So F of An will be G of An. So for F of An, you can write G of An as n goes to infinity. Now, from this, you know that G of An converges to converge to G of X naught. So you have G of X naught. Okay. So you start with F of X naught, and this is limit of this sequence F of An's, and on capital A, F and G are same. So F of An's are equal to G of An's. right? You replace f of a n by g of a n. Now, because g of a n converge to g of x naught, this limit will be g of x naught. So you have got f of x naught equal to g of x naught. Okay, you have taken a general point x naught in derived set of a, and this you obtain. So therefore, on derived set of a, f of x equal to g of x, right? It is equal to g of x for every x belonging to derived set of a. Okay, I took an x naught from derived set of a. I took an x naught from derived set of a and showed that f of x equal to g of x naught. What will be x naught? You have, if you replace x naught by x, you have f of x equal to g of x. For x naught, f of x naught equal to g of x naught equal to g of x naught. Had you taken x here, you could have got f of x equal to g of x. Okay, so on derived set of a, f and g coincide. What is a closure? A closure is a union derived set of a. On a also, f and g coincide. On d of a also, f and g coincide. So if you combine this one and this one, okay, this and 3 will give you that f of x equal to g of x on a closure. Okay, so if you combine that f and g coincide on derived set of a and hypothesis says that f and g coincide on capital A. You have got that f of x equal to g of x on a closure also. Okay, since f equal to g on capital A. Okay, so f and g coincide on capital A. On derived set of A, you can show that f and g also coincide. Therefore, on a closure, f and g coincide. Okay, that's how you have to answer this question, right? Yeah, so there is some chart. తెలియదు అబ్బా వింటున్నా అంటే 2019 బ్యాక్ క్వశ్చన్స్ మిస్సింగ్ ది continuations are what else? Okay, yeah. See, I'm not doing chapter wise. I am taking some questions. I'm trying to discuss them, right? And I am trying to explain the answers for those questions, and you have to practice these answers. I think because time is short, I think this approach helps you rather than hanging on a single chapter. Okay, that's what my objective is, right? Yeah. Next is 3b. 3b. Prove that a topological space X is compact. A topological space X is compact if and only if any class of closed subsets, any class of closed subsets of capital X with finite intersection property. In exam, you write fully. Finite intersection property has non-empty intersection. Here I am writing abbreviations to save time, but in exam you use full form. Okay, it is not family improvement or faculty improvement. No, it is finite intersection property. Yeah. So prove that a topological space X is compact if and only if any class of closed subsets of capital X with finite intersection property has non-empty intersection. Okay. To answer this question, I have to explain to you the concept of compactness, right? First, let me explain what we mean by compactness, and then I will come to finite intersection property, right? Let us take a topological space. X comma top, right? In a topological space, if every open cover of capital X has got a finite subcover, then we say that set is compact. Okay, that space is compact. What do we mean by this is said to be compact. This can be called definition. A topological space X comma tau. I mean, this is a topological space. A topological space X comma tau is compact, rightfully compact. If and only if every open cover of capital X has a finite subcover. Has got a finite subcover. Okay. Yeah. What do we mean by a cover? See, on the number line, you can take an open interval. Right? You can take an open interval. For this open interval, or rather, you take a closed interval. That will be interesting. You take a closed interval. Right? A closed interval is a closed set. Okay. For this, you can take an open cover. What is an open cover? You take open intervals. Exhausting all the points of this closed interval, right? So if you have a closed interval a comma b, and if this is union of certain open intervals, a lambda comma b lambda, where lambda varies over lambda, big lambda, then this is called an open cover for this set. Okay. If a set is covered with the help of some open sets, covered means this. This is contained. This is a closed set. Union of open sets is open. Open intervals are open sets. Union of open sets is open. Right hand side is open. Left hand side is closed. So there will not be equality unless they are a capital X or phi. So correct thing will be subset. Okay. This closed interval is a closed set. It is contained in this open set. Okay. So if you can cover this set with the help of open sets, such a collection of open sets is called a cover for this set. Okay. In general, you have this situation. If some B is contained in capital X, if there exists G lambda belong to tau such that B is contained in union G lambda, lambda belongs to script lambda. Here, let lambda vary in index at big lambda. Okay. If this B is a subset of union of all these open sets, then we say this collection of open sets is a cover for this set B. Okay. Right. And let me give you another example. We have R with the usual metric, okay, or with the Euclidean distance metric, and this metric space generates a topology, that is the usual topology, okay, and in this topology, Q becomes a closed set. The set of rational numbers becomes a closed set. Q is the set of rational numbers. This becomes a closed set. Okay. For closed set, you can produce an open cover. For closed set, you can produce an open cover. How do you take that open cover? This is contained in AI minus epsilon comma AI plus epsilon, right? Union of all these as I varies from 1 to infinity, right? Okay, where AIs are rationals, right? Okay, it need not be I could you can as well use that. Okay, here you have AIs are becoming opens. AIs are changing over Q. Okay, each AI is a rational number, right? And epsilon is a positive number, positive constant. Epsilon is a positive constant, it is a fixed constant. Okay, so what I'm doing is I have this set of rational numbers, 1/2 and 1/3 and 1/4 and so on. These are all rational numbers, right? In fact, you cannot show all rational numbers on the number line. No human being can show all rational numbers on the number line, or he can't even show you the irrational numbers. Okay, these are rational numbers. Around each rational number, you take an open interval of radius epsilon. Okay, if this is some AI, if this is some AI, you take the open interval A minus epsilon and then A plus epsilon. Okay, this is an open interval. In fact, it is an open disk centered at AI of radius epsilon. Okay, every open interval becomes an open set. So we are able to cover this closed set with the help of union of open sets. Each union of any number of open sets is open. So this is called an open cover for Q. Okay, so if in case this open cover, see how many sets are these? How many open intervals are these? Q. This set of rational numbers is countably infinite. These are infinite in number. These sets are infinite in number. Okay. If your set Q is compact, only finite of these open sets will be covering Q, but Q is not compact. So we have this situation. Right? X comma tau is a topological space, and for X you take an open cover union of G lambda. Lambda belongs to script lambda. Okay, and let these G lambda come from tau. So in a topological space, if you can cover capital X with an open cover, right? And if this open cover, if in case it is finite, it's okay. Sometimes it may be infinite. These G lambdas may be infinite in number. Out of these, if finite of them are enough to cover this capital X, okay? If this implies there exists lambda 1 up to some lambda n such that X is contained in union G lambda I, where I equal to 1 to n. Okay, right? So you start with a topological space and let it have a cover G lambda of G lambdas, where lambdas are coming from script under set big lambda. Okay, this big lambda may be infinite in number. It is interesting only when you have infinite number of G lambdas. Okay, that is when this big lambda is infinite. If in case for every cover, correspondingly, if you have finite number of G lambdas, whose union again covers capital X, then that property is called compactness. Okay. In fact, you can show that R compact sets are closed and bounded sets. See, here we defined a space to be compact, right? And then we can define subsets also to be compact. It's like this. Now we define X comma tau to be a compact topological space. Compact, T-O-M-P-A-C-T, compact topological space. Okay. And if Y is contained in X, right? In a topological space, capital X, you may have a subset Y. For a topological space, capital X, you may have a subset Y. On Y also, you can speak of topology, induced from tau. Okay. What you do is you define tau Y to be Y intersection G as G varies in tau. Okay. If you have a topological space X comma tau, and if capital Y is contained in X, you look at Y intersection G, where G varies so in tau, right? You can show that this is a topology. These sets will be forming a topology on capital Y, right? Is a topology on capital Y. Okay. See, these are subsets of capital Y. You can show that these all these sets as G varies over tau, you will be getting different sets Y intersection G's. You can say, show that all of these will be forming a topology on Y. Okay, so Y comma tau Y is a topological space. Okay, so whenever you have a topological space as X, and if Y is contained in X, you can speak of the topology on Y, and this is called a relative topology. This is called a relative topology on Y, induced from tau on Y. This is called relative topology on Y. Okay, whenever you are inside a topological space X, and if Y is contained in X, you can speak Y as a topological space in its own right. That is called you can deal Y as a topological space in its own right. That is with respect to the relative topology. Okay, when you are dealing with R with the usual topology, this absolute value metric induced topology, And you know that closed intervals a comma b, right? Closed intervals a comma b with a less than b. These are bounded. These are closed and bounded. Okay, so in place of y, you can take closed interval. So this is a topological space. This is a topological space, and closed interval, you can take this to be y. You can take the relative topology on this closed interval. You can speak whether this is compact. We can show that this is compact. You can show that this is compact. Okay, if you take any open cover for this set in the relative topology here, you can show that that open cover has got a subcover, finite subcover. Okay, so that's how. Yeah. In fact, on R, we can show that a subset is compact if and only if it is closed and bounded. Okay, so for R, if you take some D contained in R, right, you can show that D is compact if and only if D is closed and bounded. Okay, this is called Heine-Borel theorem. Heine-Borel theorem. Borel theorem. In fact, this is true in Rn. Under Rn, you can show that this is true. Right? This shows that if you in the metric induced topology, in the Euclidean metric induced topology on Rn, if you take any subset D, it is compact if and only if it is closed and bounded. This theorem is called Heine-Borel theorem. Okay, so on R, a closed, right? If you take A and B to be finite real numbers, and then this becomes closed and bounded. If you take this closed interval, it becomes closed and bounded. Therefore, it becomes compact. Okay, and if you take any other set which is not closed, it fails to be compact. Okay, so you have to understand these things, right? And then, yeah, I have to talk about the finite intersection property. Finite intersection property, FIP. Finite intersection property. Finite. This is finite intersection property. Intersection property. Okay. What do we mean by this? See, say you have, we are inside a topological space. Say we are inside a topological space, it's comma tau. Let script f be equal to set of all f lambda, where where is our lambda? Let this be, right, coming from x, okay? let f lambdas be subsets of x, and let lambda vary your big lambda. This is a collection of subsets of x, okay? If you take any finite number of these, f lambdas, if their intersection is non-empty, we say this f capital F has got FIP. Okay, if for any finite number of sets f1 up to some fn coming from script f, intersection fi I equal to 1 to n is non-empty. Okay, we say capital F, rather script f has finite intersection property. Okay, you take any finite number of entries from this script f. Say you are taking n entries, f1, f2, fn. If you look at their intersection, if this intersection is non-empty, we say this script f has got finite intersection property. You take finite number of entries from this collection, their intersection should be non-empty. This n may be varying. First, you may take 5, and then 6, and then 7, and so on. When you take 5, look at the intersection of those 5 sets, it should be non-empty. When you take 6, look at the intersection of those 6 sets, it should be non-empty. So whatever n natural number you take, you collect n sets from here, the intersection of those n sets should be non-empty. If that is the case, for every n, we say this script f has got effect. Okay. Now, what does this theorem say? What does This question saying X is compact if and only if every open cover of X has got a finite subcover. Huh? This one. Yeah. This is the question. Show that in a topological space X is compact. Show that a topological space X is compact if and only if any class of closed sets X with FIP has non-empty intersection. So if a class of closed sets has FIP, then intersection of all of those closed sets should be non-empty. That's what this says. Okay, let us prove this. Right. So let X comma tau be a topological space. Be a topological space. Right. X comma tau is compact. Why that noise is coming again? If and only any class of closed sets script F with FIP as non-empty intersection. Okay. let us prove this already. So let us assume X comma tau is compact. Let this part, first I'm doing this part, only part. Okay. This part. Let X comma tau be compact. Be a compact topological space. You take an arbitrary class of closed sets with FIP. Let F belonging to F lambda, such that lambda belongs to script lambda, be a class of why that noise is coming? So all of you please switch off your mics unless you speak. Hello, all of you please switch off your mics. Be a class of closed sets in this topology, closed sets with FIP. Okay. Let X comma tau, assume this. Let X comma tau be a compact topological space. Then you take a class of closed sets script F with FIP. Let F be consisting of F lambdas, where F lambdas vary over script lambda, be a collection of closed sets. Class means collection of closed sets with finite intersection property. Okay, let this class possess finite intersection property. Then we have to show that intersection of all these is non-empty. This class has non-empty intersection means you go for the intersection of all these. Okay, then we have to show that it is non-empty. So claim intersection F lambda belongs to script lambda is non-empty. Okay, this class has non-empty intersection means go for the intersection of all the elements in this class, that is F lambdas. Go for the intersection of them. Let small lambda vary over script lambda. Go for the intersection of them. It non-empty intersection means their intersection is not empty. This is what we have to show. Okay, let us start with negation. Let us say this intersection is empty. let if possible, intersection F lambdas, lambda belong to script lambda be equal to empty. Okay, we have to show this intersection is non-empty. You start with the negation of this. Negation is that this is equal to this. Okay, negation is that this intersection is equal to empty. Now you take complement on both sides. This implies intersection F lambda belongs to script lambda, complement will be equal to phi complement. Okay, you take the complement operation on both sides. What is by de Morgan's laws? What is complement of intersection? It is union F lambda complement, as lambda belongs to script lambda. Z is equal to what is complement of empty set? What is complement of empty set? It is X minus Phi complement is x minus
A.
X minus
Anyone said, sir.
Phi.
A or
A complement is x minus
X minus
complement is x
5.
minus
A, sir.
A.
Ah.
Phi complement is x minus phi.
Y.
Y.
Is equal to x, right? Is equal to x. So phi complement can be written as x. So this is an open cover. Therefore this contains this. This contains this. So and what kind of sets are f lambdas? F lambdas are closed sets. F lambdas are closed sets. F lambda is a class of closed sets. So each f lambda is a closed set. Okay. So f lambda is closed. So it's a complement. What is complement of a closed set? Is it open?
Open, sir.
Open set. So f lambda complements are open sets, and this gives you that this union contains x. Therefore, this becomes an open cover for x. Okay. Since f lambda is closed, lambda belongs to f lambda is closed for every lambda. Okay. Implies f lambda complement is open. Okay. F lambda complements are open sets, right? Now, because of this, because of this, the f lambda complements become a cover for capital X. So one implies that f lambda complements as lambda belongs to lambda is an open cover, for capital X. And we are given that capital X is compact. What kind of set is capital X? Capital X is compact. Okay. Therefore, compactness gives that this cover will have a finite subcover. Right? X is compact. Implies there exists lambda 1 up to some lambda n for some natural number n such that union f lambda I equal to 1 to n contains capital X. Okay, right? Now, because capital X is compact, out of this cover, you can take only finite number of these whose union is again a cover. Okay, this happens because your set capital X is compact. Now, right? Each f lambda I is subset of X. Each f lambda I is subset of X. So you can take equality here. There is no harm. You can take equality here, right? You can replace this by equality. So f lambda I equal to this, right? Now you apply complement on both sides. So what do you get? So this implies that union f lambda I equal to 1 to n complement will be capital X complement. Okay, I have taken complement on both sets of these. So union f lambda I complement is equal to X complement. Okay, now again by De Morgan's law, this is intersection f lambda I complement, where I equal to 1 to n is equal to, what is X complement? What is X complement? X minus X is how much?
5.
5. Very good. 5.
5.
Okay. Now these. Am I correct? No, I mistake. What is the mistake? Yeah. Here, f lambda complements is an open cover, so we should take complements here. Okay. I forgot this complement. F lambda complement. F lambda complements. These form the open cover, and out of these, I have to take finite number of it. I forgot this complement right? Symbol. Okay. I should take C here. So I get C here. So f lambda I complement will be f lambda I. Right? F lambda I complement will be f lambda I. Okay. Right. So you have right here. I forgot to take complement f lambda I complement. Now you go for complement on both sides. Right. You get intersection f lambda I is equal to X complement. Okay. So here you have got finite number of entries in this from this collection. from this collection of closure sets, right? We started with the collection f lambda, lambda belongs to lambda of closure sets. These are closure sets. Okay. Out of this, we have got finite subcollection whose intersection is empty. But what is our assumption? Our assumption is that this possesses finite intersection property. Means, however finite number of entities you take from this collection, their intersection should be non-empty. This F consists of FIP. Means what? However many finite number of entities you take from script F, their intersection should be non-empty. Okay, but you have got one finite subcollection whose entry is empty. So this is a contradiction. So this is a contradiction. Okay, to the hypothesis, to this hypothesis. If you call this 2, okay, this is hypothesis again. So for this hypothesis, we got a contradiction. Okay, this is a contradiction to the hypothesis 2. Therefore, why did this happen? It happened because of this. Okay, because of this, we took the negation of this, and that has led us. We took the negation of this, and that is this. That has led us to contradiction. Therefore, this claim should be true. That intersection of f lambda belongs to script lambda should be non-empty. Therefore, this is correct. Therefore, 3 is true. Therefore, 3 is true means what? Therefore, script f is having script f has non-empty intersection. Has non-empty intersection. Okay, has non-empty intersection. As non-empty intersection. TION. Okay, so we assume that capital X is a compact topological space. For that, we took an arbitrary class of closure sets f lambdas with FIP, and we tried to show that it has non-empty intersection. So we have to show this, and so we assumed with negation of it, and then we arrived at a contradiction. Therefore, our assumption is wrong. Therefore, this is not equal to this. Means this is true. Okay, means this has non-empty intersection. Okay, so in a compact topological space, every class of closure sets with FIP must have non-empty intersection. Okay, so this part is over. Now let's assume this one and obtain that compactness. Let's take a topological space wherein every class of closure sets having FIP has non-empty intersection. Okay, this hypothesis will be sufficient to prove that capital X is a compact topological space. So yeah, so let us prove this part. This is if part. Let script F be equal to f lambda, such that lambda belongs to script lambda, be a class of closed subsets of capital X. Let this be a class of closed subsets of capital X, closed subsets of capital X with FIP. Let F be an arbitrary class of a closed sets of X with FIP. Let this have non-empty intersection. Okay. So I'm assuming that in capital X, whatever class of closed sets you take with FIP has non-empty intersection. I'm assuming that if I take an arbitrary class of closed sets, script F, consisting of f lambda, lambda belongs to lambda, has FIP, and then this script F has non-empty intersection. That I am assuming. So I want to show that capital X is compact. Okay, this is what I have to show. So how to show some topological space is compact? To take an open curve for this and show that it possesses a finite subcover. So let G lambda, let G lambda belongs to, where lambda belongs to, you can as well use some other subscript G eta, where eta belongs to delta. Okay. That's small. Okay. Yeah, let us go for eta. Right? Let G eta, where eta belongs to delta, be an open cover. Be an open cover for capital X. Okay. For this, you start with an open cover. Means what? Capital X is equal to union G eta, where eta belongs to delta. Okay. I'm assuming these are open sets. Open cover means each G eta is an open set in this topological space capital X. I mean, also assume that this is an open cover, means union of all of them is equal to capital X. Okay. Now, out of this, we should be able to produce a finite subcover. It is we should be able to get a finite number of G etas whose union is again capital X. That's what our objective is. Okay. So, yeah. We wish to show that this open cover, let me call this script G. This open cover script G has a finite subcover. Okay, we wish to show that this open cover has got a finite subcover. Okay, this is what we want to show. Suppose this is not possible. Means what? Let it be not possible. Let it be not possible. Not possible. Means what? Means what? Means what? There exists. Now, yeah, you give a number for this, 4. From here, what do you get? From here, you take complements on both sides. What do you get? From 4. So 4 implies what? That X complement is equal to union G eta, where eta belongs to delta complement, right? we have this, you take complements on both sides. So X complement is union of G and eta complement. So X, I have gone to some of the next page. Let me bring it to the previous page. So 4 implies, is it 4 or 3? 4. So I'm taking complement on both sides. X complement is union G eta complement. So X complement is equal to union G eta, where eta belongs to delta complement. Okay. So this implies what? What is X complement? X minus X, that is empty set, is equal to union G eta complement, where eta belongs to delta. Okay. By De Morgan's laws, X complement is X minus X is pi. So, and G eta is an open set. G eta is an open set. G eta is open. Therefore, G complement is closed. G eta complement is closed. So, this is a set of, if you look at all G eta complements, as eta varies over delta, this is a collection of closed sets. And it has, this is another mistake. When you take complement, this union becomes intersection.
Intersection.
I think my fuel is over. I'm losing concentration. Okay. So intersection G eta complement. So thus right? Thus script F dash. Let me call it script F dash. This is equal to G eta complements, where eta belongs to script delta. Is a class of closure sets with empty intersection. Okay. So G eta complements are closure sets, and if you go for the intersection of all these, it is empty. So this class has empty intersection. So what is our assumption? Our assumption is that in X, if you take any class of closed sets with FIP, it will have non-empty intersection. Means what? FIP gives you non-empty intersection. If you take a class of closed sets, if this possesses finite intersection property, that will be giving you non-empty intersection. If you negation of this gives empty intersection. Negation of this gives you finite not FIP. It does not have FIP. Okay. If you take negation of this, see, this is called statement. These are two statements. Statement 1, S and T. You can take S1, S2 to be statements. S1 statement 1 implies statement 2. What is contrapositive of this? It is S2 complement negation. S2 complement gives you complement of this. Negation of this gives you negation of this. Okay? S1 implies S2. These two are statements, S1, S2. Right? What the contrapositive of this implication is negation of this implies negation of this. These two will be equivalent. Okay, so if you have got a class of closed sets with empty intersection, it must not have FIP. So this is a class of closed sets with intersection. So this implies, right? You can give the this hypothesis number 5. So 5 gives you that it has non-empty. It does not have FIP. So 5 gives you that F dash has no FIP. It doesn't have the finite intersection property. What does it mean? What does it mean? It does not have finite intersection property. Having finite intersection property means what? If you take any finite number of edges from here, their intersection is not empty. Their intersection is non-empty. Finite intersection property means for every n intersection G eta complement where eta I equal to 1 to n. Okay, this will be non-empty. Finite intersection property means if n is any natural number, and then if you take finite number of edges from here, G eta I complements where eta I varies from 1 to n. These are n in number. Their intersection is non-empty. That's what is meant by FIP. So it has no FIP means what? It has no FIP means what? Negation of this means what? There exists an n, a natural number n naught such that intersection is empty. Intersection G eta I equal to 1 to n. Eta I equal to 1 to n naught is empty. Okay. What is negation of this? Replace for every way there exists and n not belonging to n such that replace inequality by equality. So non-equality by equality. So intersection of G and I complement where I equal to 1 to each n naught, where eta I equal to 1 to n naught is equal to empty set. So from here you take negation on both sides. Yeah, this is again complement. Complement comes here. You take complements on both sides. You have union G eta I where eta I is equal to 1 to n naught is equal to capital X. What is complement of this? X minus 5 is x. Okay. So you apply complement on both sides. So you replace intersection by union and G eta I complement is G eta I and replace this by complement that is X. So we have got a finite subcover. We started with an open cover G eta I for X. We started with an open cover G eta, right, where eta belongs to delta, which is an open cover for X. And for this, we have got a finite subcover, right? We have got finite number of entries. Eta I varies from 1 to n naught. These are n naught in number. Their union is capital X. So this is a finite subcover. Therefore, capital X is compact. Okay. We started with an arbitrary open cover for capital X, and we are ended up with a finite subcover of it. Okay, of that open cover. This is a finite subcover because these are finite in number. These are n naught in number. Therefore, our X is compact. So what we did is this one, right? These two are equivalent. Yeah, right in if you have a topological space, compactness is equivalent to that any class of closed sets with FIP has non-empty intersection. These two, compactness and this property, are equivalent. This is a criterion for compactness. Compactness can be described in terms of closed sets in this way. Okay, right? Of course, you have the definition of compactness. That is, every open core has got a finite subcover. That is equivalent to this one in terms of closed sets. Okay, so with that it completes. See, in exam, if you practice this, you can write down in less time. Okay, I am trying to explain to you. My effort is that you understand the subject and then try to do honestly in the exam. That's what I am trying. See, okay. Next is 5A. Next is 5A. 13. Yeah. 5A. Prove that every compact subset of a metric space is closed. That is, every compact subset of a metric space. Subset of a metric space is closed. Okay. Every compact subset of a metric space is closed. Yeah. What is a metric space? Can I have some water? What is a metric space? Hello? What is a metric space? Is there anybody? Yeah. So, let us take a metric space X comma D. Okay, let us assume this is a metric space. Okay, and let F be contained in X be compact. Let F contained in X be compact. Okay. What is the metric space? What is the metric space?
X3.
Yeah. What is it? When do you say this is a metric space? What is D? It is a metric. What is a metric? What is a metric? D of X comma Y is greater than or equal to D of X comma Y is equal to
D of Y comma X.
D of Y comma X. D of X comma Z is less than or equal to D of X comma Y plus
D of Y comma Z.
D comma D of
Y comma Z.
Y comma Z. Triangle. Okay. If you have a function D on X cross X with these properties, and not only this, I forgot this. This is equal to 0 if and only X is equal to Y. Okay. Right. D of X comma Y is 0 if and only if X is equal to Y. And then D of X is D of Y. And then okay. Please switch off your microphones which you speak. These three properties give you this can be treated as a subproperty of X. So these three properties make X as a metric space. Please switch off your microphones. Please switch off your microphones. Please coming like the welding machine noise. That is humming, I think. Okay. Let us take capital F to be a subset of X. And let us take it to be compact subset. Okay. See, we are taking F as a subset of capital X and we are assuming it is compact. And compactness is defined for topological spaces. Right? Every metric space induces its topology. Every metric space induces its topology. In that topological space, F has got relative topology. And so F can be treated as a topological space in its own right. Okay. And as a topological space, we are assuming capital F is compact. Now we have to show that capital F is closed. Okay, in capital X. Okay, I will explain the main idea. Right. It's okay. So, so this is capital X. Of course, it is a topological space. It is a metric space, right? And out of this, you get a topological space. Every metric uses topology. That is the usual topology. Out of this metric, you get open sets. Collect all those open sets. Those will be forming a topology on X. That is right, denoted by tau. Okay. Now you are taking F to be a subset, right? You're taking a compact subset F. You're assuming F is compact. And now we'll show that this compact subset, right? This whole thing, this one, this is F. This is F. Okay. We'll show that this F is closed. This F is closed, right? How to do that, right? How to do that? How to show a set is closed? How to show? So claim F is closed. F is closed. How to show a set is closed? We have to show complement is open. To show F is closed, we'll show that its complement is open. Okay. Closedness is defined in terms of complements. A set is closed if and only if its complement is open. So look at its complement. You take an element in its complement. Which color? Green. I will go for green. Yeah. Let X be an element in the complement of F. It is outside this red portion. I'm taking an element small x in F complement. I'm taking X from F complement. I'll show F complement is open. How to show something is open? We have to show this X is an interior point. Means we have to show an open neighborhood around X, an open sphere around X, which is completely contained in F complement. That's what we have to show. So what we do is, corresponding to this X, you take any F, you take an arbitrary point F in an arbitrary point Y in capital F. So Y is in capital F, X is in F complement. Small x is in F complement. This all is F complement. Let me give different shade. That blue shade, this is F complement. This is F complement. This whole thing is F complement. Okay. This all F complement. Blue colored, the portion is F complement. Okay. I have taken an element small x in F complement. Now, so x is in F complement. This blue portion is F complement. So, and small y is in F. So X and Y are distinct. X and Y are distinct. Okay. In a metric space, you can separate any two distinct points with the disjoint open neighborhoods. In a metric space, you can separate any two distinct points. X and Y become distinct. X is not equal to Y. These two become two different points because Y is in some set F and X is in its complement. So those two cannot be equal. Okay. And in a metric space, any two distinct points and different points can be separated with the help of open neighborhoods. So you can take an open interval around this and an open interval here and an open interval here. Such that these two open intervals are disjoint. You can call this GY and you can call this some GX such that GY intersection GX is empty. This is possible because you take the distance, for example, you take the distance between X and Y. What is the distance between X and Y? It is d of X comma Y. It is d of X comma Y. Okay. And you now around Y, G of Y can be taken as S. You take half of this distance, half of d of X comma Y, and around Y. You take the open interval centered at Y of radius half of this distance. Okay, right? So we'll be taking this portion. We'll be taking this open disk centered at Y. Of course, if you want small, no problem. Okay, let it go outside. No problem. Around X also you take similar thing. That is, this is right. S of X of this of this distance d of X comma Y. Okay, so around this you are taking this open interval. Okay, this open interval. These two open disks don't intersect. Okay, That's that's how in a metric space, if you are given two decision points, you can separate them with the help of open sets. Open disks become open sets. Okay, so you can separate these two x and y with two disjoint neighborhoods. Okay, now what you do is you will be allowing this y. See, if you take a y from f, you will be getting an open neighborhood. So you let this y vary. You let this y vary, and this gx also will be varying. As you vary y, gx also may vary. Okay, gy and gx may depend on each other. So what you do is you look at this cover union of gy as y varies in f. Okay, you look at union of all these open disks, all these open disks gy's as y varies in capital F. This becomes an open cover for f, and f is compact. So out of this open cover, because f is compact, it possesses a finite subcover. Finite number of gy's, maybe n in number. You can get gy1, gy2 up to gyn, whose union is again in the f. Okay, so you will get finite number of entries of y's, right? So I'll draw in the figure. So you have this situation, right? So what colors we are using? Okay, red and green. So this is your f, and x is green. This is x, right? So there will be finite number of entries y1 and y2, and you are using green. Yeah. So gy1, gy2, gy3, gy4, gy6, gy7, gy8, gy9, gy10, gy11, gy12, gy13, gy14. Okay, so f is contained in union gyi, where i varies from 1 to n. There exists finite number of entries gy's whose cover, whose union is a cover for f. Okay, this happens. And corresponding to each gy, you get a gx here. Okay. So this may be gx1, this may be gx2, this may be gx3, this may be gx4, this may be gx5. Okay. And here what you do is you form intersection gxi's where I equal to 1 to n. Okay. Right. These have center, right? These open neighborhoods, gy's are open neighborhoods of yi's. These y1, y2, and so on. These are entries in f. So corresponding to each gy, there will be a gxi, right? You form the intersection of all these, right? These are finite in number, right? These are open sets. Intersection of finite number of open sets will be open. This is an open neighborhood. This is an open neighborhood of x. Okay, right? And because you have taken gyi intersection gxi is empty, this gives you that union gyi where I equal to 1 to n intersection this one gxi where I equal to 1 to n. This will be empty. Okay, because you have chosen gyi gxi in such that they are disjoint. From that you will get that this set intersection this set will be empty. Okay, so the intersection of all these will be in f complement, will be disjoint from this open cover, and that open cover contains f. So this open neighborhood will be disjoint from f. Therefore, this will be contained in f complement. So this open neighborhood will be contained in f complement. So for x, we have got an open neighborhood in f complement. Therefore, our so this x becomes an interior point. Therefore, f complement becomes an open set. Okay. So therefore, f becomes closed. That's how we prove. Okay. So you can put all this in words, right? So for y belonging to f and x belonging to f. See, if your f complement is empty, there is nothing to prove. Empty set is empty set is both open and closed. So F will be open. Okay. If in case it is non-empty, you have to proceed. So if F complement, case one is F complement is empty. There is nothing to prove. So this is open. Okay. Case two is that your F complement is non-empty. So there will be an X in F. So let this Y vary. For Y belong to F and X belong to F, there exists GY. There exists open GY, GX such that GY intersection GX is empty. Okay. Let a small y come from capital F and X come from F complement. Okay. So there will be two disjoint open neighborhoods GX and GY such that the intersection is empty. Okay. Now GY such that Y belongs to F is an open cover for F. F is compact implies there exists N not belonging to capital N such that union GYI where I equal to 1 to N covers F. Yeah. Okay. So this implies covers F. Yeah. Now Further, small x belongs to intersection GXI where I equal to 1 to N. And GXI intersection GYI is empty. Okay, that's how we chose. These are empty sets. They are disjoint sets. So we have this intersection of all these GXIs is an open neighborhood of X. And because of this is true for all I equal to 1 to N. Okay, because of this, we have that these imply that union GYI where I equal to 1 to N intersection intersection GXI where I equal to 1 to N is empty. This implies intersection GXI where I equal to 1 to N contains X. Okay, this contains X and this will be contained in F complement. So this will be disjoint from this. This is an open cover. This is an open cover for F. Therefore, this will be disjoint from capital F. So it will be sitting inside F complement. Therefore, F complement is open. Okay. So because F complement is open, F is closed. Therefore, F is closed. Okay. So that's how you can prove that in a compact, in a metric space, a compact subset has to be closed. Okay. So that's how you can do this. And yeah, in fact, after maybe in a couple of classes, I will define you various properties of separation. T1ness will be there and T2ness will be there. Okay, T2ness is about topological spaces in which you can separate any two distinct points with the help of two distinct neighborhoods, right? X possesses a neighborhood Nx and Y possesses a neighborhood Ny such that they are disjoint. Okay, and such a space is called T2 space. A topological space is said to be T2 if and only if every pair of distinct points X and Y from capital X is separated with the help of disjoint neighborhoods. Okay, and this property is called Hausdorffness. Hausdorff, H-E-A-U, Hausdorff, Hausdorff, H-E-A-Dorf, D-O-R-F-F, Hausdorff. Maybe I'm wrong in spelling. Hausdorffness. Okay, it is also called T2ness. Okay, Hausdorff. Such a space is called a Hausdorff space. Hausdorff was a mathematician. Okay, and in fact, we can show that every metric space, every metric space is Hausdorff. Every metric space is T2, right? So, and there are certain metric spaces which are not T2. Oh, I'm sorry. There are certain spaces. There are certain topological spaces which are not T2. Every metric space is T2, right? Every metric space is T2. Yeah. So these are metric spaces. They sit inside T2 spaces. Okay, these are metric spaces, and there are certain topological spaces. There are certain topological spaces which are not T2 spaces. Okay, there are certain elements which are in the complement of T2. There are certain spaces which are not T2 spaces. Okay, this we'll look at later. Right? Can we stop here? Hello.
Yes, sir.
Yes, sir.
Are you able to follow me? It's a kind of Ekapatra
Yes.
name. We say it is Ekapatra name in Telugu. I am going on teaching something. I don't know whether you are able to understand or not. Are you able to understand me? Hello? Are you able to follow me?
Yes, sir.
Yes, sir.
Okay, okay.
Yes, sir. Yes, sir.
Tomorrow I'll come to 4:30 session. Let's leave it. Okay. Can I stop here?
Okay, sir.
Bye bye. Goodbye.
Bye.
Goodbye.